Hello, I'm Ross. I work for a small consultancy called Reimagine It. We do a lot of technology transformation, but a lot around networks. Some of you know me. My background was when I started out leaving school, I worked backstage in theatre, so I've got an appreciation of all the audio problems. Ended up in IT, ended up in networking for one of the big groups, was there for a long time. For about 15 years doing networking, and I left that, and since that I've been playing in public sector and education markets, which surprisingly have a similar amount of challenges. So that's a bit about me. This is going to be fast and high level. Networks are different for everybody, so take the bits that work for you. Don't read too much into the bits that are deeper. We might need to have a talk over lunch if that's the case. So what are we going to do? I want to talk about what ifs. I like what ifs. So what if you could fix your network failure slowly so the organization didn't notice? You could upgrade core devices without impact. You could improve security and resilience, and you could adapt to changing business needs rapidly. And you could offer flexible solutions, making tasks easier and more adaptable. And you could focus on the future rather than just keeping the lights on, and imagine what that could enable you to do. Before we get into the fun stuff, here's some symbols. Hopefully most of you know what these are. We've got a symbol for server, workstation, laptops, that could be a playout system, audio devices, switches. Switches work at layer 2. We'll talk about layers in a second. That's your MAC addresses and things like that. Routers, they move across layer 3 boundaries. That's where IP addresses really start to come into play. And firewalls, they secure things between them. Now, you can get hybrids of various ones of these, but we'll keep it nice and simple as separate at the moment. Terminology, local area connection, that's your LAN, that's within a building. Normally a lot of switching happening there, maybe a bit of layer 3. Wide area connection, WAN, lots of buildings. Unicast, packets that go from one place to another particular place. Multicast, one to many. BUM, the most humorous networking term there is, which is broadcast unknown unicast and multicast. That's the switching terminology. We'll talk about it a bit later on. Precision time protocol, you may find this in some of the audio over IP protocols. It's a really good way of the network learning variations in the master clock. Quality of service, that's when we actually apply a profile onto the traffic so we can decide what traffic goes out on the network in what order. If you've got audio traffic, you don't want it to be stuck behind someone surfing Facebook. So but the problem with quality of service, if you put too much of it, you fill up your buffers on your switch, and then you run out of traffic and everything falls over. So there's a rule of thumb of about 30% of your quality of service, sorry, your bandwidth quality of service. Virtual LAN, VLAN, it's a switching thing. Turns your switch into multiple switch. You can put them all down one port by using tagging if you want to. Bandwidth, we've already covered that. Latency, how long it takes a packet to get somewhere else. Jitter, the variation in the latency. If you're sending lots of packets, how much does that time vary? And convergence time, how long does the network take to fix itself? Ideally, we want that nice and quick. We want it really quick, under a second if we can, ideally, so the listener doesn't hear. However, that's difficult to do when you're on a wide area network. What do I reckon? 5 seconds? If someone's driving along in the car when they're most likely to be able to change a channel, I reckon I've got about 5 seconds of tolerance of silence before I'm going to go and find another channel. Network layers, the OSI network model. In networking, 5, 6, 7, that all happens inside this PC. I don't care about that. Number 1, physical layer. That's where we've got our fiber, our copper, our Wi-Fi, 5G like we had earlier. OTN, there's all sorts of fun things in there. Data link layer, MAC addresses, switches. Kind of multicast happens there away. Layer 3, TCP/IP. So this is the IP bit of this. This is IP version 4 and IP version 6. Now, we're not going to talk about version 6, but I do think people need to start thinking about it because it will eventually become a bigger thing. Transport layer, this is where TCP is a transmission control protocol. It's a bidirectional conversation. You send a packet, you expect something back. UDP is a unidirectional protocol, and that's you send a packet out, you don't expect something back. By definition, all multicast has to be a UDP packet. And the only reason we worry about layer 4 is we use those for marking packets for QoS. So, when you're looking to buy hardware, what are we looking for? You get what you pay for to a certain extent around budget. Now, you can get really cheap things from your Curry's PC World. You can get the Netgear Pro AV line that adds some useful stuff. You can spend moderate amount of money on a switch, and then you can spend lots of money on a switch. There are manufacturers now that means you don't need to spend as much as you would have done in the past to get an awful lot of power. So there's a wide spectrum of things you can get there. Firewalls especially, you can get incredibly powerful firewalls for not a lot of money now. Features, does it support everything you want? PTP is a really good example of this. It might say it supports PTP, but does it support transparent clock, which is your layer 2 thing? Now you then say, oh, I want to do PTP across layer 3. Now they might say, I do that, but most vendors only support the unicast variant of it. Now if you're doing AES 67, you want the multicast variant of it. So you cut down the number of devices that you've got available for you. Vendors like using different terminology, so don't expect them all to call the same thing. It's really helpful. They also, if you've got 2 different product lines from the same vendor, they probably call them different things across that as well, because why not? They also like changing the defaults. So defaults on one vendor will be different to another vendor. So that's always fun to kind of unpack. Standards. Now, you might think it's a standard, the vendor's going to support it. Yes. I can reference 2 examples, one in broadcast and one in finance, where we had a device that you'd powered up, and you wouldn't get multicast out of it. The network would reject it on a particular piece of kit. Restart the service, you get multicast. And you go, that's a bit odd. Turns out the device was sending packets prior to it getting an IP address, which meant it was sending a source address of 0.0.0.0. Now, a very, very, very large player in the networking market doesn't implement the standard correctly and forwards those packets. Everyone else has the thing that says, thou shalt not forward packets that are sourced 0.0.0, so it wouldn't work. So just be careful that although it says it supports the standards, you need to do some fairly extensive testing. And can it perform what you want it to do? Network hardware has software parts and hardware parts. If you've got a feature in hardware, it's nice and fast, normally down in the nanosecond switching technology. You get up into the software, you're fighting with everything else that's happening in that switch and the software thing. You can get things that start breaking because the switch is busy, so you don't really want to get in there. Legacy protocols, how many bits of weird audio kit have we got that are still running on 10 meg ports because they won't support anything else? Less and less switches are going to be supporting that in the future. How long is it going to be sold and supported for? This comes back into our sustainability as well as just being able to fix it if it goes wrong. If it's stopped being sold next year, it means it's going to be stopped being supported in a couple of years. Buy something that's going to last. And openness. Does it use open standards to talk to other things, or are you looking at proprietary standards? There is nothing wrong with using a proprietary standard if there's a good reason to do it, but just be aware that you are locking yourself into a vendor. So, resiliency. Why do we want to do resiliency? Well, things break. We all know about diggers hitting the odd bit of fiber. Transceivers go down quite frequently. We want it to be efficient. We want things to happen quickly and gracefully. There's more and more audio over IP in the network. We want to be able to fix the systems when it breaks, or we want to be able to do security upgrades and things like that. We want to be able to take something out without taking the broadcast chain out. And security. We want to limit any impacts. We want brand protection. So, planning a network. We will get to interesting stuff in a bit, I promise. Set yourself some objectives. Actually work out what your requirements are. Discover what you're going to do. Work out what works and what doesn't work. How does it fit in with your organizational strategy? That's a good one to actually get in. It's easier to get the money if you can go to the board and say, this fits in with your strategy. Budgets in that. Think about your budget, but also think about the budget. What happens if you break something? Because if you go off air, you could have a commercial impact. What's actually that loss? How likely is it? Therefore, is it worth spending a bit more on a particular bit of kit? Have a think about what you've done, design it, and think about scaling for the future, and then actually just kind of make it happen. Many people who know me are going to laugh that I'm talking about documentation in this level of detail, because I historically have not been very good at this. However, service definition. Actually write down what the thing you're doing is supposed to be doing. Make some high-level and low-level designs. The important thing about all of this is keeping it up to date, of course. Think about a decision log. None of this needs to be complicated. Just write down as things come along, and you change your mind about something. So someone in 10 years go, why did you put that setting like that? It's written down somewhere. Do you need to have a service request so that you actually understand that if someone requests a new VLAN or a VLAN change, that you have a ticket for that, or there's a particular process? How do you add a new site? Think about it, write it down. And do you need to do anything particular about change process for this service? So what have we gone to now? And don't forget, you might need to train some people, do lots and lots of testing, try and break it as much as you can. How are you looking after it? Do people need command line access? Are you doing it through a web UI? Do you need role-based access control? Back up your configs, monitor and alert. but don't monitor and alert too much that you get flooded with alerts and false alarms. So, hey, diagrams. Triangles are better than squares. Why do we like triangles? If we have a fault on this one, if I take out this link here, packet has to go all the way around. If I do the same here, we only add one hop at layer 3 into the triangle. So that's why we like triangles, because you get less convergence, which means it can fix itself faster. So we've got a lovely router and a switch. Router at the top, switch at the bottom. That's very good, but actually we can get single points of failure here. So we've got all our devices connected here, and that switch, if that switch goes bang, we've got a problem. All of that's gone. However, this audio device has probably only got one power supply and one network port. Laptop almost certainly does. Server, you might get a bit more lucky with, and might have something that can support something else. All of that is single points of failure. Power could go, the device could go, the cabling could go. Someone who has a detailed knowledge of something could go. People are single points of failure too. So we want to try and get rid of them. So let's add another switch. Now we can go, we've got something plugged in here, and if it goes wrong, we'll go and move it over to here. That's okay, but actually let's try and beef that up a bit, because that cabling could go. So let's stack them. Stacks are great in principle. They can take a long time to fail over. However, why I don't like stacks in this particular scenario is generally, if you want to upgrade them, you have to down the entire stack. If you've got 10 studios plugged in your stack, you've got to turn them all off at the same time to do an upgrade. Not the best idea. Got some use in an office where you can actually take out an entire floor in an evening when no one's there, but maybe not in broadcast. So we're going to put 2 links in. But now we've created a loop because packets are going to go bing, 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 bing. So we don't want to do that. Fortunately, most sensible switches have spanning tree, which puts one of the links in a passive state for us. But it'd be better if we could use that bandwidth, which is where we get link aggregation groups, or lags. Now, this doesn't automatically double the bandwidth because we have flows. So if traffic is going here, it will be assigned to one or the other. So you can still only max out a particular flow on a particular link. The algorithms that do that vary and can generally be changed. So if you had 2 10 gig links, you're not going to get your server over here talking at 20 gig to the other side on a single flow. It has to be multiple flows. We can add spanning tree into that. So we can add a third switch with a bit of spanning tree. But if you've got nice switches, you can do multi-chassis link aggregation. So, yeah. And then you can... So all we've done now is we've got a standard lag on this one, and then it's connected to 2 systems upstream. This is great. And if you use LACP, it properly interrogates the link and will verify that everything's working before it adds it in. There is some caveats with this. You want to do this for resilience, not bandwidth. This could send flows either direction. But our switch here on the left, if that gets a flow in it, if this link is available, it is always going to send packets down here. So you are not going to double your bandwidth. But this one could be sending return packets all the way around the houses. So just bear in mind that you do multi-chassis lag, VPC in Cisco language, CLAG in NVIDIA language, for resilience, not for bandwidth. You can do it with lots of switches at the same time. You can put MLAG on MLAG. And then you end up with something which is the traditional core distribution and access setup. So we have a core on the site, we have a distribution on the site, so you have as many of these as you need for the access switches. There are traditional ratios that you use for this. So these uplinks, the number of ports you've got here, you're looking at 20 to 1 going to your distribution. You've got 48 1 gig ports, you're looking at 2.4 gig uplinks. That's all right for most traffic. Bear in mind that if you start doing something like big video, you might want to drop that to maybe 12 to 1 or even lower. But once you get to 40 gig uplinks, unless you're pushing a lot of data around, that's an awful lot of bandwidth. You'll be hard pushed to get that off servers in time. So think about how much uplinks you really need. And between the distribution and the core, they normally say 4 to 1. Just bear in mind again, high volumes, you might want to tweak that. This is really resilient, and it gives us a lot of advantages. And if we just kind of scale it back a bit, if we're thinking about this in the studio, if you have a studio on this switch and a studio on this switch, if anything happens in the studio, you lose your mixer surface, you lose the switch, just go to your backup studio. Just keep it self-contained, and if anything breaks, just move across. You could put 2 studios on there, but then you risk 2 going on that point. But that was a way that I would recommend doing it, splitting it up per studio. Don't put half Studio One's kit over there. Otherwise, if you lose a device, you've just got a mixed system that doesn't really work. So we'd talk about security. 10 minutes to go, let's go. Media is a big old target. We know this. Many of you will have experienced moments where someone has said something on air and immediately you get a DDoS attack or something like that. It's high profile. People will be looking to get in, so think about that. We do need to be pragmatic about security. If anyone is an InfoSec specialist and tells you to do an incredible amount of detail about something, they've probably never had to do it in real life. And it probably will cause you more grief than actually, so you need to be a step back and be pragmatic about what's going to give you the best results in the most efficient way. All too often, people don't apply security because of that, because they think it's too complicated. And hopefully, by the end of this, you'll get a better idea of what level you can do that will give you a pretty good level of protection. Human error. Network engineers make mistakes. Ask many people in this room about me. And also, how many of you trust all your presenters to not click that link in that email they're sent? So we talk about defense in depth. That's your software stuff, your firewalls on your machines, your antivirus, all of that. I would recommend anyone who's bored to have a good read of EBU R143, which gives you a very realistic appraisal of the security of some of the devices that will be connected to your network. It's an interesting read, and it will probably make you think about what you're doing in security space. So one of the ways we can do this is segmentation. And we want to reduce the attack surface, and we're going to isolate our network by function. We can do this from compliance, so we can stop people looking at stuff that they shouldn't be. Big bit of this is about risk reduction, so we can reduce this, and we can do this physically or logically. And let's look at a realistic way of how we can apply this to a live network. Grossly simplified, but hopefully you'll pick up the idea. So we've got a switching infrastructure here. We've got an admin team that are based over there on the right. We've got a service desk. We've got some shared services up the top, and we've got some studio stuff going on. So first of all, let's get rid of the admin team. They're easy. All their stuff's in the cloud. They don't talk to anything else. So we're going to stick them behind a firewall. They now can't talk to anything else on the left. Let's move the service desk. They're easy. They just need to talk to everything, but we don't want things to be able to talk to the service desk. And our shared services, well, we can move them again because that's clearly defined stuff. So actually, we end up with a firewall config that says, permit established connections, service desk can talk to anywhere, admin have selective access to shared services, studios have selective access to shared services, and we block everything else. So we're now in a place where if someone does something daft in the admin department, they can't affect our studios, which is always good. Next stage of this is what's called micro-segmentation, which is where we start taking it a bit further. And we apply access lists on the switch. The key here is we don't want the admin of these switches to become cumbersome. We don't want access lists that are going to cause us grief in the future. This firewall's got a lovely GUI for managing access lists. Don't make your life difficult by having huge, complicated access lists on the switch. So we come along, and over here, we just put an admin policy that says we permit established connections, and we say that admin device 1 cannot talk to admin device 2, but they can talk to anything else because the firewall's controlling it. Now, if a device in the admin network gets a nice bit of ransomware, it can't physically talk to the other device in the admin network, and we've immediately stopped that lateral movement. We can do a similar thing up in here. We can go, we permit the established connections. We're going to permit a level of access within the segment because we need our devices within the studio to talk to each other. However, we are going to allow traffic to other segments, and it hits the firewall. How does that work in reality in a broadcast world? We've got Studio 1, Studio 2, playout server up there on the right. So notice how these switches do not have any access lists. It's only in our audio distribution switch. We're permitting the established connections. We're permitting multicast audio distribution between those zones so that Studio 1 can send audio to Studio 2. We're allowing SQL access from Studio 1 up to the playout server, and we're allowing file access to the server. And we're blocking traffic between Studio 1 and Studio 2. And then from our playout stuff, we're permitting the established connections, we're permitting the multicast audio distribution, because we may need something up in our server world, and we're blocking the other traffic. So this can establish a flow that way, but the playout server cannot establish something back. Something happens over here, and someone clicks a dodgy link, Studio 1 can be taken out. They could get as far as the playout server, but that playout server can't get back to Studio 2. So if you've then got cached audio and cached playout facilities, you can keep going while someone rebuilds that playout server from a backup, And this is essentially dead on the network, unplug it, and you can do a slow rebuild on it. So the next thing for this is you get to network fabrics. Now, network fabrics are currently a generation of technologies that enable us to virtualize the entire network. So everything's virtualized. They're incredibly agile. There are two big technologies out there, some others as well, but VXLAN is a big one, or an 802.1aq, which is shortest path bridging. They simplify management, and hopefully you'll see why in there, and they're ideal for segments. So with a fabric, you can have a switching infrastructure, and actually, you only ever need to touch the edges. So here, we've got a VLAN ID of 5 on these two sides, and we give it a fabric ID, and actually, I don't need to do anything in the middle. The fabric takes care of it. In fact, on the far side, I can link to that same VLAN, but give it a different VLAN ID, because it doesn't care as long as the fabric ID is the same. That enables us to span VLANs across multi-sites. You can also go one step further, and you can mix layer 3 stuff into it as well. So this bit can be a fabric ID between those two switches. You can have a layer 3 gateway on there, which jumps into a VRF, which comes out here and comes out as another fabric ID over that side. That way, everything in the middle doesn't change. You only need to change things at the edge, and you can adapt your fabric to whatever your network needs it to be, which gives you an enormous amount of flexibility that you don't need to change your core. It means it's more stable, it's more resilient, because you are not applying changes in the middle. So, back to the what ifs. You could fix a network failure slowly so the organization didn't notice. Well, we can do that by actually removing our single points of failure using things like mlag, spanning tree. Rapid spanning tree will go down to about 50 milliseconds if you're lucky. You could upgrade core devices without impact. Same thing, remove those single points of failure. You can take a little bit of the network down, do the upgrade. You can improve security and resilience. Well, we've looked at how segmentation can do that. And you can adapt to those business needs and flexibility by using fabrics. And that then frees you up to be able to think about what your organization's actually doing now and in the future, and what that can enable you to do. And that is whistle-stop networks.